Now it's my pleasure to introduce Cliff Young, who will be our next speaker. Cliff is a software engineer in the Google research team where he works on co-design of deep learning accelerators. Cliff also was one of the designers of the Google initial TPU, and so he has a long history in terms of how the industry has progressed in this space. And so with that, it's my pleasure to introduce Cliff for the next session. Cliff, you can share when you're ready.
Yeah, I believe I screen shared, and I got an interesting prompt from Zoom but I disabled your audio. So it looks like you guys can hear me. Can you hear me?
We can hear you, but I don't see the picture yet or your slides yet.
Okay. It says I'm screen sharing. So I can stop the share and restart. The trick is of course, the muting aspect of it, which could be frustrating. Hold on just a second. All right, share screen, tab.
Okay, we are seeing, it says you started screen sharing and it shows a black screen for us. And you're muted. There you go. Yep. Perfect. We see you now.
Yep, you're just muted, Cliff. We can see the slides.
Perfect.
I'm wondering if the moderator has the power to unmute Cliff.
I just did.
Excellent.
At our end, at least. System claims he's unmuted, but he's still supposed to be muted at his end. So, don't you love technology?
I definitely love the technology. Sure. Any luck now with hearing me and seeing my slides?
Yes.
Okay. Yes. So the trick was I had to pause audio share from my slides in order for you to hear me again. So woo, Zoom. So it's great. I guess it has the switches. All right. Look, sorry, took more time than expected. Happily, I cut my slides down, so I do not have as great, wonderful detail as Rob just did. Rob, great talk, by the way. Thanks for that. I aimed to focus down rather than giving the usual TPU talk, and I'm happy to, in Q&A, talk more TPU details if that's the relevant thing, to focus on the greenness and energy efficient aspects of this conference, because that seems like what's front and center. So this is kind of a particular slice through TPU land and Google's view of things, where my agenda is, yes, accelerators are actually green, which may not be obvious because we're putting liquid cooling and Mongo heat sinks on these machines. And beyond that, I think cloud accelerators are greener. And there's a little bit of preview of coming attractions from Google and papers that are coming out, but there's surprising data about how green you can be depending on where you site your data center. So I'll touch on that just a little bit in this talk. So Google builds TPUs largely for our own use. They're also available as cloud TPUs to rent, with varying degrees of success about that. I have some pretty pictures of 4.5 generations of TPUs in this slide. The one on the far left is the one I worked very closely on, the initial TPU, which was an inference-only machine. And for its 2015 debut, it was pretty hot stuff with 92 teraops at only 75 watts of power consumption. The subsequent machines have all been training capable. They're all floating point enabled, or at least bfloat 16 floating point enabled, which is actually a power hit. Floating point is tougher to do than integer arithmetic, and that has caused us to take a little bit of a step back on energy efficiency. But what we got for that is the ability to train and also the flexibility to run in inference exactly the model that we ran in training, where the first TPU had a whole bunch of difficulty in quantization for deployment, where basically if you train in floating point, which you still have to, there's no algorithmic breakthrough yet for training in fixed point, then you want to deploy in a fixed point device, whether it's a mobile sort of edge device or the first generation TPU. That translation to fixed point is actually wonderful for energy savings, but hard from an algorithmic and system design perspective. So that's been a break on inference deployment for a while. Anyway, what I've listed below the TPUs, aside from showing the pretty pictures in air and water cooling and so forth, is the teraops per chip, and then the effective watts per chip. And the bottom row of figures is actually sort of tera operations per watt, where TPU-v1 is actually still doing pretty well at 1 teraop per watt, or 1.2. The floating point machines took a step back and are slowly crawling back, with Moore's law continuing to deliver still slightly better silicon processes for us. So we're inching back with 0.16, 0.27, and 0.78 tera now flops per watt. But I think the contrast to draw is actually against more general machines, because these are indeed specialized machines. And if you, I didn't show a general purpose CPU, but if you go back to the Haswell machine, that's a contemporary of the first TPU in 2015, it's maybe 100 watts and 1 teraop. So that number would be 0.01 teraop per watt instead. And so an accelerator is a huge step up from that. That's the first part of my thesis, that accelerators are green. CPUs are, of course, responding. So nowadays you can buy pretty awesome Sapphire Rapids machines that are, I think, in the 100 watt per socket, 100 teraflop per socket range. That's a great solution. And that's closer to that one number. Might even give a TPU a run for its money at this point. And so there has been response from the CPU vendors. But I think that the energy efficiency ball is kind of ours to lose from the accelerator perspective. We can build green accelerators. For the large scale training that is front and center now, the giant models where there's a space race going on among different things called GPT-3 and 4 and all sorts of names that I can't remember, Rob pointed out that we're using giant machines to train these giant models. Like if you got 1 trillion parameters, you're going to need a cluster worth of machines. And Google's been doing that since our second generation TPU, our first generation training machine. There's a first gen cluster with only 4 racks and 256 nodes. At the top of this slide, I guess third generation TPU, second generation training machine with 8 racks, 1024 nodes in the bottom of the slide. I don't have a picture of the TPU v4 pods, but those have 4K nodes, and they're kind of another 8 rows deep behind this set of wires and additional wires you can't see. The wiring is pretty gnarly for doing this giant machine training. And you can imagine the corresponding, just take the watts numbers from the previous slide and multiply by node count. That's just the chip wattage, not the overhead for all the power supplies and the cooling systems and the transduction from air to water, if that's going on, actually not in the training machines. So this adds up to real power. And the scale of this is, of course, warehouse scale. I think Google touts warehouse scale computers, and this is one of our pretty data centers. I forget where this one's located. Normally I show this slide and say it's great that a data center can be pretty, but I think in the context of power, one of the questions is how many megawatts does a building like this represent? And it's tens of megawatts. I think our standard data center building at Google was 20 megawatts for a while. I think we're upping that now and building 30s and 40s and maybe even 50s. That's a decent amount of power, a decent number of accelerators. And these pods are now a significant fraction of the entire floor space or the entire power budget of one of these data center scale buildings. So this is industrial machinery, right? Like, I mean, I think people worried about how large scale heavy industry was departing the United States maybe 20, 30 years ago. It's come back in some ways. In some ways, this is heavy industry, although one nice thing is that it's relatively green heavy industry in that we can use green power to run this, and it's not actually full-blown industrial processes with big stacks some of the time. And that's maybe the second part of my talk. I got 4 minutes left. So this slide is basically about, wow, there's a lot of interest in ML and green versus red AI, about the environmental impacts of how many cycles are we burning, how many watts are we burning to train these giant models, and are they a significant fraction of gross domestic power usage? Are we going to melt the ice caps or kill all the polar bears as part of this? Some of the extrapolations are really quite dire. The most recent one that I think is in the dire thing sounds Malthusian to me, in the sense of Malthus, who predicted that population growth would destroy civilization sometime in the 19th century because exponential growth unchecked would just, we'd reach some terrible resource scarcity result. And so if you do this from a past, look at the past and just multiply out in the back of the envelope, it is indeed terrifying. I think part of the thesis of this particular article is that getting an increase in or improvement in error rate requires exponentially invested costs. I believe that's true for the scaling approach to models, but I don't think it's true for AI as a whole, because I think we're just barely at the beginning stage of AI in terms of efficient methods. I think I have other slides that I'm not showing today about. I think we have great steam engines, and steam engines are unbelievably effective at replacing muscle power, but they're not the most efficient thing, right? There are electric engines today that are way more efficient, and we understand thermodynamics, so we can do a much better job. So, but anyway, to the end of the world predictions, like there's some pretty dire stuff about like, are we going to burn in Austria or in New York City or whatnot as part of doing this? So this dialogue about, are we going red or are we green, is out there. And in my remaining time, I'll just do a preview. Next month, Google and a bunch of like really senior famous people here will be releasing a paper on archive, and it'll be coming out in actually computer, talking about carbon footprints of ML training and talking about sort of how big Google's scale is, what fraction of our work what fraction of our power budget, in fact, goes to neural network training. And I thought I'd preview a little bit about that, not give you all the results. And I've sort of fuzzed a bunch of the figures to talk about how do you think about where your power is going in training. And let me mention 4 different factors and apologize to Mark Hill for stealing his 3 C's thing and renaming it the 4 M's for ML energy efficiency. The 4 M's that I have that contribute to how energy efficient you are in training are, first of all, model. If you look at the jump from transformer, which is the basis of the current giant model revolution, to primer 4 years later, it's a 4x energy improvement for similar accuracy. If you change machines, if you buy a really great NVIDIA machine from 2017 and compare it to our latest TPUs or the latest GPUs, that's more than a 10x efficiency improvement in terms of what work you can do for the same amount of power. That's not just Moore's law, that's also design in the machines that we're building. My third thing is kind of a force fit. I call it mechanization, but it's actually data center efficiency, or what people label PUE. Google's standard data center is at 1.1. Like that's basically you pay 10% over what you're actually powering the chips with to run that whole data center. Industry standard is probably more like 1.6 or 1.7. And so that delta is another factor of 1.4. And the last M I have is maps. Where you do your work actually is a huge delta in terms of the greenness of the power. It turns out that Oklahoma, where Google has a bunch of data centers, has continuous nighttime winds. And continuous nighttime winds means we can use wind power, which is entirely green. And so if you look at the percentage of time a data center is able to access green power, it's highly variable depending on where you are. I think Singapore is terrible because it doesn't have natural power resources in the same way that Oklahoma does. And that can vary from like 100% green or almost 100% green to like only 20% green, because that's what you're getting out of your photovoltaics. That factor is another 5x. If you multiply these all together, the deltas from where we were 4 years ago till now are over a factor of 250. And so I feel like, yeah, we should definitely pay attention to the planet scale, nation scale, big company scale amount of power we're putting into these models. But I also think we're evolving rapidly. We're rapidly working on the efficiency front, and all is not lost as long as we pay attention to these efficiency things. Sorry, ran over 1 minute, but would the moderators like me to do one question before going on to the next person?
Oh, absolutely. We have time left. So I think you have a path to 250x. So we just need to find another 4x to get to the 1000x that John laid out earlier in the session, but it was fantastic. You should patent the 4 M's before Mark comes back after you. Let's see. In terms of questions, the window I have doesn't show any specific questions. I don't know, Mark.
There is a Q&A. There's another window. I can show you how to get there later, Brad, but there's a Q&A.
Okay.
About retraining on this redundantly, right? Slightly different object. Yeah, okay. I don't know how to do the cross-company one. I think that's a really excellent question. I guess I have 2 answers. Some of the giant models are actually designed to train once and then redeploy many ways. They're kind of zero-shot models. You train GPT-3 once, that might be expensive, but then you like post fine-tune it to do a particular translation task or Q&A task or whatnot, and that's a lot cheaper. That's one awesome way of sort of amortizing that. The other thing is, you're absolutely right about like reuse of data sets. Like I kind of wonder how many MNISTs are going at a time inside of Google. And MNIST is small enough that, maybe it doesn't matter that we've got, everybody has their own private copy of MNIST and you're rerunning it on a thing. But what about Common Crawl or one of the other bigger data sets? Like, shouldn't we build a system level solution that, if everybody is actually training on Common Crawl, maybe our randomization and our disk accesses should be put together and we should group those Common Crawl things. This is history of computer systems in general. Like, do you want your personal workstation or do you want a batch system that has common utility efficiency? You could build batch training systems within an enterprise like Google or another cloud provider, and maybe it has a little bit of scheduling or latency hookup where you got to catch the time when your particular training run data is available on the network. But that's a potential area for savings that I think is hot for research. Nobody's actually ever deployed things that I've heard about. That was the one I saw. Are there other questions? Or actually, now I'm really like 15 minutes is awfully tiny slot, so maybe I'll pause.
Could I ask just a brief question?
Yes, please.
I think what's really interesting is that, you know, the architectures that are emerging as great learners are at the same time a lot less energy efficient by this trend. And maybe a general question for today is, of course, we all know this famous fact that the brain does this with an extremely small amount of energy. And that seems to be an architecture issue. So obviously, it's capable of learning in a very efficient way at an extremely small energy expenditure. And that seems to be an architecture issue. What worries me is that, of course, the trends are opposite. So it seems that we're not really paying attention to the architecture issue as much as we are to the, you know, percentage of learning. So that trade-off seems to, just a, you know, do you have a comment? I mean, that trade-off seems to be almost neglected, yeah.
Yeah, lovely question. I think what you said could apply both to model architecture and to computer architecture, although I think you were initially motivated by model architecture. I think to the biologically inspired thing, absolutely. Like, you know, my brain is a dim bulb at 30 watts or 90 watts or something like that, and yet I seem to be able to learn things on few examples in ways that our machines don't know. And that is an inspiration. It's also like terribly frustrating. Like, we really don't know how actual biological learning works. And what we're doing with our brute force steam engines may not be what we're doing 50 years from now. I would love to see those breakthroughs. That might be another revolution. To the interplay of model and computer architecture, though, I think there is efficiency, and the sparsity is there in different forms, although not necessarily the form that you want. Like a bunch of these giant models are sparsely activated. They're a mixture of extracts models. They have routing, so only a tiny fraction. I think primer is 8% of weights get touched by a given model example, and so that's, you know, a factor of 15 there of savings versus our classic mode of touch every weight with every example. There's also coevolution. I mentioned that like TPV2 was efficient energy-wise. Transformer in some way can be viewed as an adaptation for, well, I can't do what I want to exactly with attention or attentive things, but if I have a TPU, I can do that in bulk by just throwing matmoles at it. So I feel like the researchers are tuning to the machines that we're able to build to the extent that NVIDIA gives us awesome fine-grained 2-for-4 sparsity, and the researchers then pick that up and run with that, right? We will get to better efficiency. So I think that it's not over. I think there's the, you know, as engineers, there's the frustrating stuff of what can we do right now with the machines we have? And then as scientists, the what do we wish we were doing for better learning algorithms, like better model structure and better computer architecture, all that is on the table. Speaking optimistically, I'm really enjoying the ride. Absolutely yes to what you're doing. Please do more. Like if you build the sparsity revolution that makes all of our machines obsolete, because I think, well, you know, Rob and I might be a little sad about our business model disruption, but we would get to build cool new machines. And so, like, you know, keep us in business, change the algorithms. The worst thing for a computer architect is for the algorithms to stagnate, but happily that's not what's happening. The algorithms are evolving just as fast as the architectures.
Thank you. And by the way, great talk.
Thank you.
If I could just interject for a second, and yeah, Cliff, that was actually really good. I think there's way more we can do about efficient architecture and improving things, but the evolution of the neural nets is so radically fast. I mean, I'm not kidding when I say the state of the art changes dramatically every 6 months. The evolution is so rapid, it's really hard to spend the energy on those optimizations. Nonetheless, I think as an industry, we do spend a huge amount of energy on that. I think it's hidden by the advancing, you know, when the demand is increasing 10x per year, it's hard for anybody to notice the efficiencies you're baking in.
Yeah, thanks.
Excellent. I think with that, maybe we transition off into the next session. Thank you so much, Cliff, for your talk.